Thanks for watching AI Weekly Update from Henry AI Labs. This week we'll start with a really great thesis from Thomas Kipf on deep learning with graph-structured representations, presenting neural networks for explicitly structured data like social networks, the World Wide Web, or chemical molecules, and algorithms for implicitly structured data like images. This thesis also presents a great description of why we should be interested in structured representation learning for the sake of generalization. MIT News covered an interesting paper presented in ICLR 2020, Meta-Learning Curiosity Algorithms. I think it's really cool to see AutoML applied in a new way like this to discover curiosity or intrinsic motivation components to improve exploration and reinforcement learning. A somewhat shocking paper from ICLR is a critical analysis of self-supervision, or what can we learn from a single image. This paper shows that you can augment one image 1 million times and get a similar performance in the representation of early layers of a CNN as if you were to do this with different images. This shows that many current self-supervised learning tasks are all about augmentations and don't really leverage massive datasets. The rebirth of robotics describes Covariant, one of the hottest companies in deep learning and robotics, from the lens of an investor in the company. Researchers from UC Berkeley have been doing a lot of interesting work with fabric manipulation. This article describes different algorithms to do things like fabric smoothing or folding, concluding that model-based methods are the most promising paradigm for this. Offline reinforcement learning, tutorial, review, and perspectives on open problems is a really great overview of the applications, primary challenges, and most commonly used solutions in offline RL. AI and efficiency from OpenAI details a trend in less compute to reach a fixed level of performance on ImageNet classification and similar gains for translation and solving games with reinforcement learning, showing that algorithmic advancements are outpacing hardware gains. Exploring Bayesian optimization from Distill is a great interactive visualization to get a better sense of Bayesian optimization through the lens of black box gold mining. Uber AI has recently released a blog post to summarize the novelties in the enhanced POET algorithm. MIT News has also published an article describing the steerability of GANs and searching for how generative models generalize along the dimensions of different data augmentations such as translations or zooming in. We will also look at a great article from Madison May on pragmatic ML about pattern exploiting training to overcome challenges of limited labeled data in text classification and natural language inference. Finally, we'll look at the deformer, a slight architecture variant to speed up question answering inference. If you haven't already, please subscribe to Machine Learning Street Talk. This week, Tim Scarf, Yana Kilcher, and I will be reacting to the ICLR 2020 keynotes from Jan LeCun and Yoshua Bengio. Deep learning with graph-structured representations is a really great overview of machine learning with structured data. The thesis begins by describing structure and human cognition. This idea is that we often think, reason, and communicate in terms of concepts, abstractions, and relations. A natural way to represent this kind of information is in structured form as a graph, where we have nodes and edges that connect these nodes to each other. If we had structured representations in deep learning, it would dramatically improve generalization because we would have a sense of how to recombine these random variables. There are two parts to this thesis. The first is dealing with data which is explicitly structured, such as social network graphs, the World Wide Web, knowledge bases, chemical molecules, or citation graphs. Kipf has worked on many models for this kind of data, such as graph convolutional networks, graph autoencoders, and relational graph convolutional networks. These networks are used to do things like classify entire graphs or individual nodes or edges. An example of this could be a citation graph. We insert a new research paper into the graph and connect it to other papers based on the citations. The citations are how we form the edges to the other research papers in the graph. Now we might use a graph neural network to classify this new paper based on the category, whether it's an optimizer paper or a data augmentation paper or an AutoML paper, based on the edges in the graph and the features of the nodes that is connected to. The second part of this thesis looks at how we can learn implicit structure from sensory data such as images. One paper listed that I think is really interesting is contrastive learning of structured world models. A world model is used in reinforcement learning for planning or learning in simulation. This approach learns structured world models by predicting future states, or S prime, from a state action pair SA. The structure is trained using contrastive learning between a positive true latent transition Z prime after you map from the high dimensional state S prime into Z prime, and the other latent representations from the buffer. Tying these ideas of deep learning with graph structured representations together, Kipf presents 5 research questions that guided the work in this thesis. Can we develop and efficiently implement deep neural network based models for large-scale node classification tasks in graph structured datasets? Can graph neural networks be utilized for link prediction and unsupervised node representation learning? Can deep neural networks infer hidden relations and interactions between entities, such as forces in physical systems? How can we improve upon neural network-based models that infer event structure and latent program descriptions in sequential data? Can deep neural networks learn to discover and build effective representations of objects, their relations, and effects of actions by interacting with an environment? This thesis presents a lot of interesting work in machine learning with structured data. This looks like a really promising direction for generalization. Structured representations make it easy to disentangle dense representations and take apart individual variables. The thesis gives the example of an elephant with wings. We can easily imagine this combined concept, even though we have likely never encountered such a creature. I'm really excited to keep studying this, especially in relation to a lot of the talks that Yoshua Bengio has been given about this kind of structure and how it helps with generalization. Yoshua Bengio presents the sparse factor graph and the consciousness prior. If you're interested in these ideas and how it might help with generalization and better deep learning models that learn to reason, please tune into Machine Learning Street Talk, where Tim Scarf, Yana Kilcher, and I will be reacting to this ICLR 2020 keynote talk. If you're interested in graph neural networks and natural language processing, I highly recommend checking out this article, Transformers Are Graph Neural Networks, where you'll see that there are a lot of similarities between how graph neural networks do message passing and aggregating information from the previous input layer, and how transformers have this kind of sparse attention. There's also a lot of similarities with the tasks they perform. You could think of classifying an entire sentence based on its sentiment as a graph classification task. You could think of doing something like a pronoun disambiguation as the same as doing node classification. And edge classification could be something like entity relations with natural language. So there's a lot of interesting connections between deep learning with structured representations and these explicitly structured data like social networks and stuff, and natural language processing tasks. MIT News published an article about meta-learning curiosity algorithms, a novel and exciting take on AutoML and intrinsic motivation presented at ICLR 2020. Curiosity, or intrinsic motivation, is a component of reinforcement learning algorithms that helps with exploration. These techniques augment the reward signal to promote the agents to either search for novelty or explore states that they had badly predicted the transition into. This paper designs an evolutionary search to combine operations that form a curiosity algorithm. These algorithms modify the true environment reward and present a new reward to the RL agent. This paper searches for diversity in environments explored, going from grid navigation to Acrobot, Lunar Lander, and Ant Hopper. One way to do this is by having a polymorphically typed genotype. This helps deal with different inputs, such as an image pixel grid or a vector state representation. They introduce other techniques to increase the computational efficiency of large-scale evolutionary search, such as predicting performance from the structure of the Curiosity program. I think this is a really exciting paper, and it's cool to see all the areas that AutoML can be used to search for new ideas in deep learning. Data augmentation is one of the most commonly used regularizations or inductive priors for computer vision. We commonly take our image datasets and rotate them, flip them, or crop them so that our classifiers are invariant to such transformations. Self-supervised learning has been learning representations by filling in the blanks or denoising corrupted data, usually corrupted with these augmentations. A critical analysis of self-supervision, or what we can learn from a single image, is a fairly surprising demonstration of the current state of self-supervised learning tasks. A common example of this is the rotation task, where we take an image and rotate it either 90, 180, or 270 degrees, and then a classifier predicts the rotation angle from the original image. Well, we usually look at millions of images in this rotation task and assume that all these images have been useful for the representation learned. However, this study shows that you can take the same image and augment it 1 million times and get similar performance in the early layers of a convolutional network when doing representation learning with self-supervised tasks like rotation network or the big ByGAN model. This shows that self-supervised learning is augmentations, augmentations, augmentations. I highly recommend watching this great presentation of this paper from ICLR 2020 from one of the authors of the paper. One of the most exciting companies in robotics and deep learning is Covariant, led by Peter Abbeel. Covariant recently raised a $40 million Series B investment. This article offers a perspective about Covariant and its potential applications through the lens of an investor in the company. The author describes the appeal of robots that can perform a wide range of applications, the shocking advanced technology, the use of domain randomization for sim-to-real transfer, and the application of picking and placing objects in distribution centers across the world that struggle to find and retain labor for this task. 4 novel approaches to manipulating fabric using model-free and model-based deep learning and simulation describes research from Berkeley Labs led by Peter Abbeel from Covariant and Ken Goldberg. This article describes robots that deal with fabric like towels or t-shirts and potential applications such as dressing assistants for senior care, folding laundry, bed making, or manufacturing. The article presents 2 model-free based papers, both of which are trained in simulation and use domain randomization of cloth physics, color, and lighting for sim-to-real transfer. The article also presents 2 model-based methods, one which plans in the raw pixel space and another in a compressed latent space. The article presents that model-based methods have more potential for generalization to a variety of tasks, provided that the learned models are sufficiently accurate. The key difference between model-free and model-based reinforcement learning is that model-based models have their own transition model. They can predict the state S prime from a given state action pair, whereas model-free methods just learn from experience without explicitly constructing a model of these transitions. Differently from the debate between model-free versus model-based RL is online versus offline reinforcement learning. The reinforcement learning problem is most commonly studied in the online setting, where we have an agent that interacts with the environment and learns through this direct interaction with the environment. Offline RL, also described as batch or data-driven RL, aims to learn without actually interacting with the environment. Section 2.3 of the survey describes some applications of offline RL. The most obvious one that comes to mind is things like robotic cooking, where you don't want the robot to break dishes and waste food in order to learn how to cook. Another application mentioned is decision-making in healthcare, where the actions represent available interventions like diagnostic tests and treatments, and the observations represent the patient's symptoms and the results of diagnostic tests. Obviously, we need an agent with some sense of this before it gets to act in the real environment. The survey presents some of the core challenges of offline reinforcement learning. The most obvious challenge is that of exploration. We have to assume that the dataset of trajectories contains transitions that illustrate high reward regions of the state space, because it's impossible to do any kind of discovery. The survey also describes the challenges of counterfactual or what-if queries and distribution shift. This is a really great overview of the different techniques used in offline RL, a paradigm which has definitely been gaining a lot of interest and traction. OpenAI published an interesting blog post about AI and efficiency. This comparison is done by holding performance constant. Say, how long does it take to get to 78% ImageNet classification accuracy rather than how much computing does it take to beat the state-of-the-art accuracy at the time. They cite that this has been decreasing by a factor of 2 every 16 months on the ImageNet classification accuracy benchmark. Compared to 2012, it now takes 44 times less compute to train a neural net to the level of AlexNet, whereas Moore's law would yield an 11x cost improvement over this period. This is showing the benefits of algorithmic advancements, such as innovating from AlexNet to MobileNet and EfficientNet. The authors further describe a 61x compute reduction between the sequence-to-sequence approach to machine translation and the recently introduced transformers architectures, as well as an 8x reduction from AlphaGo 0 to AlphaZero and 5x from OpenAI 5 to OpenAI 5 Rerun. The article further describes efficiency gains such as inference speedups, or how long it takes to make a prediction with a trained model, in addition to the time required to train the models from scratch. Distill has published a really great interactive visualization of Bayesian optimization. The article frames the problem around black box gold mining. We can drill at an X location to find out how much gold is there, but it's expensive to do so, and we don't get gradient information from the point. The article describes 2 components of the gold mining problem. Active learning is where we search for high information points to drill at. Bayesian optimization is about drilling at locations that show high promise about how much gold is there. The article provides great visualizations about where uncertainty reduction algorithms based on Gaussian processes want to drill across the iterations to reduce uncertainty about where the gold is. In Bayesian optimization, we use the Bayes rule, where we combine our prior expectations with the posterior that we're seeing. So first we choose a prior to model the gold function with, and then we use an acquisition function to reason about the posterior or what we've sampled. The article goes on to describe different acquisition functions, such as probability of improvement or expected improvement. And in classic distill fashion, there are visualizations where you can adjust hyperparameters, such as the epsilon for probability of improvement, to get a better sense of how the algorithm works. This will definitely be the article I go to when I'm looking to get a better understanding of Bayesian optimization. Uber AI has just released a blog post about their enhanced POET algorithm. In my opinion, this is one of the most fascinating papers in all of deep learning. POET is this idea of goal switching or stepping stones on the way to complex behaviors. We have this coevolution between the agents and the controllers that control how the bipedal walking agents walk in the environments, and then we have the different environments. So as we evolve the complexity of the environments and as we're training the agents, they co-evolve and adapt such that it can goal switch and go from one environment to another environment, and in this way it has this open-ended formulation of learning the stepping stones along the way to controlling a walking agent in a really complex environment. The enhanced POET makes the algorithm more general, with enhancements to the POET algorithm and a measure of progress for these open-ended algorithms. I think this is a really exciting paper, and I highly recommend checking out this blog post. We study generalization in classifiers by seeing how well they label images they haven't seen before or reacting to explicitly chosen out-of-distribution images. I think that generalization is more interesting to study in the context of these generator models. Generator models produce data and are a better representation of the visual data manifold, which is another way of describing where natural images sit in the impossibly high-dimensional and complex space of all possible images. On the steerability on generative adversarial networks looks at how well we can extrapolate different augmentations from the training set, such as searching for the latent vector z that can zoom in on a generated dog image or perform an X or Y translation on a generated image. The authors show that the generators from GANs are able to do this fairly well, and adding data augmentation to the training process further facilitates this. Pattern exploiting training is an interesting way to leverage pre-trained language models for text classification or natural language inference tasks with limited labeled data. Take two sentences, T1 being, "This was the best pizza I've ever had." T2 being, "Pretty bad, you can get better sushi down the road for half the price." Now a new sentence comes along. "Pizza was average, not worth what they were asking." If you're labeling the new sentence based on similarity to T1 or T2, it helps to have extra information about the task, whether it's about classifying it on sentiment or if it's about a review that mentions price at all. The authors generate data in pattern exploiting training by augmenting the language model to fill in the task. For example, prefacing a text with "it was underscore." The language model fills in the underscore of the mask with either terrible, bad, okay, good, or great, and this provides additional data for fine-tuning these models. This achieves huge gains in limited data text classification settings like Yelp sentiment reviews. Deformer, decomposing pre-trained transformers for faster question answering, is the latest approach to speeding up inference with these transformer language models. This paper shows that you don't need to fully attend over the input sequence in the early layers of these transformers, rather splitting the attention up to self-attention over the question and then self-attention over the answer, and then doing the global attention at later layers in the transformer. This speeds up question answering by over 4.3 times, and with the simple distillation-based loss, they only lose 1% in accuracy by doing this.